stress strain, elongation, then linear strain, lateral strain, change in length, change in diameter, change in width. So this was yesterday's lecture, in which we have seen for a single bar, that is material is same. Now this is composite section. Composite section means it is made up of two materials. For example, if this is timber or wood and this is steel, that is, this is steel and this one is inside. Cross section of timber is circle and cross section of steel is, this is timber, cross section of steel is hollow circular cross section, that is one circle inside circle, and diameter of inside circle is diameter of timber. Now let this be subjected to force P. Now when force is applied P, you have to find, now this P will be taken, some part of P will be taken by steel, some part of P will be taken by timber, or in other words, one material and second material. You can say one material second. Now we will see what are the equations or how to find. Suppose this has length L and this is fixed at 1 and P as shown. Now there are two equations. Let force taken by timber be P T and force taken by steel be P steel. Now the equation is total load is P, therefore first equation is P total load equal to P taken by timber plus P taken by steel. This is one equation. Now there are two unknowns, so we want two equations. Out of that, this is first equation. Out of that, P we know. P will be given. Now second equation, even if P, part of P is taken by one material, part of P is taken by another material, still due to application of load, whatever is the change in length, this change in length, let us say delta, is same. This is second equation. Now let PT be load taken by material T. Let AT be cross section of timber and let ET be modulus of elasticity for timber. Similarly, let AS be area of cross section of steel, ES be modulus of elasticity for steel. Now as delta is same, we have equation. What is the change in length for timber? PT, PL upon E, PT into L, L is common, upon AT, which is area of cross section of timber, into ET. This we know, but this we don't know, this we don't know. Again, this we know, this we know, because dimensions will be here. Now this is equal to ES into L, because L is common, upon AS into ES. Now again understand. Load taken by timber, length, total length, area of cross section of timber, E for T, P for steel, A for steel, E for steel, and L is long. Out of that, L gets cancelled. So this is second. Out of that, P we know. Included P will be there. So if you solve these two equations, that is, let us say, if you eliminate one, you can find P, that is load taken by timber. After that, substituting in other equation, you will get load taken by steel. This is the composite section theory. Once again, total load is equal to load taken by one material plus load taken by other material. And secondly, change in length is same for one material and other. This is because there is a bond. Why this theory behind this? It is a bond. That means even if materials are different, they don't act differently, but they act in unison. That is, they act as same. This is the problem. To give example, we know RCC, that is concrete and steel. Concrete and steel, this is good example for civil engineers. Concrete and steel are bound together and they act. So how if you see cross section is for example concrete, or in other words, or beam concrete, and there will be steel inside. So this is the cross. This is concrete, and this is steel. So there is a bond. Bond means what? They act as same. When force is applied, there will be change in length, but that change in length will not be different for different materials, but it will be same. But load taken by one material and load taken by other material are different. So this equation. So once again, one equation, load taken by 1 plus load taken by 2 is equal to total load and change in length also. So by this you can solve any type of problem which is of composition. I will take another simple example on yesterday's theory. For example, now in this case, material is same, but cross sections are different. Now let us see how to find or what is the problem. For example, there is a load applied P and length of, now material is same, this material and this material are same, but cross sections are different. L1 is the length, L1 is the length for same material but cross section different, whereas L2 is the length for this part. And the problem is find change in length or change in length equal to. Now let E be modulus of elasticity or Young's modulus. Total length is L1 plus L. Therefore, in this case, it is not like composite section, but material is same. So load taken by for part 1 is P. Load taken for part 2, that is for length L2, is also P. Therefore, to find change in length or to find total delta L equal to, this is simple example. Now delta L, which is the total change in length, is equal to delta L for part 1, that is for L1, plus delta L for part 2. Now let we don't give numerical we can take. Let A1 be cross section area for part 1 and A2 be cross section area for part 2 and L1 length for 1, L2 length for 2, whereas E is modulus of, and modulus of elasticity, as material is same, material is same, E also is same. So this is equal to PL upon A, PL upon A equal to P into L1 upon A. What is A for part 1? A1. PL upon A. E is same. Plus, this is the term delta 2 P into L2 upon A2, because area of cross section is different. This area of cross section is different. This area of cross section is different. Into. So if you substitute, you will get total change in time. So like that, if cross sections are different, for example, I'll just give you the figure. Now you have understood how to find change in length. There can be change in length for different areas of cross section. For example, and similarly, here also there is a force P, L1 length, L2 length per part, L3 length per part, and P is the force. Force is same. So how will you solve the problem? E is modulus of elasticity. A1 is area of cross section of 1. A2 is area of cross section of 2. A3 is area of cross section. So for delta L equal delta L1 plus delta L2 plus delta L. And on similar lines, we will write the equation. It is equal to P into L1 upon A1 plus P into L upon A plus P into L upon A3. झालं आणि नुसतं एक एक्झाम्पल सांगतो वेगळ्या प्रकारचं सम डिफरंट टाइप ऑफ प्रॉब्लेम इज देअर which is somewhat, I will not take actual numerical, but I will give you theory. Now here area of cross section is same. But the forces applied at different parts of the same length This is the length. Are different. For example, if this total bar is divided into 3 parts, now here area of cross section is same, but the forces are different. How? For example, and length also is same. Area is same, length is same, but forces, that is force taken by part 1, force taken by part 2 and force taken by part 3 are different. To give example, for example, for part 1 there is a tensile force. For part 2, for example, there is a compressive force. Actually in numerical you will understand. And for part 3, for example, again there is a tensile force. So this is P1 of tensile length. This is P2 of compressive force. And this is P3 of again tensile. To find net, we won't say total, but we will say net change in or delta. So this delta will be equal. This delta will be equal to change in length for part 1 due to tensile force. So it will be equal to P1 into L1 upon A1, or A is same. And now what is the change in length for part 2? It is compressive force. So change in length will be negative or length will decrease. So second sign is P2 into L2 upon A. Again for part 3 it is tensile, so plus P3 L3 upon A, because AE are common for part. So only for part 2 there is compressive force. Due to that, change in length will be negative. This is tensile.
That is
So
P1,
length will be
P2 plus sign, plus or minus?
minus, because it is compressive. This is minus. This is compressive force, and this is again tensile. Due to tensile force, length increases. Due to compressive force, length decreases. In numerical example, you will more understand.